Alright, welcome. In this video, we're going to start our unit on rational functions. And so I'm going to start off by telling you what a rational function is. A rational function is defined by the ratio of two polynomials. So we're going to be really interested in, discussing the polynomial in the numerator and the polynomial in the denominator, how that affects the overall function, using a lot of the tools that we developed in the last chapter. Okay, so we will find the y-intercept on the graph of a rational function exactly like we find the y-intercept on the graph of any other function, and that's going to be by plugging in 0. Okay, so if f is the rational function defined by f of x equals x minus 1, what's the y-intercept? Okay, so just like always, we're going to grab this thing and fill it in. We see y-intercept, we know we need to plug in x equals 0. Okay, so I'm going to be interested in finding f of 0, which is going to equal 0 minus 1 divided by 2 times 0 plus 3. And this is going to be equal to negative 1/3. Okay, so the y-intercept is f of 0 equals negative 1/3. And also, like before, we're going to find the x-intercepts on the graph of a rational function by setting the function equal to 0 and solving for x. Okay, so if g is the rational function defined by g of x equals x squared minus 16 over x minus 16, what are the zeros of g? And so just like always, zeros of g, that means like where y equals 0, the x-intercept, we're going to set g of x equal to 0 and solve. Alright, so we're looking for where x squared minus 16 divided by x minus 16 is equal to 0. And I am assuming a little bit of familiarity with solving equations that have x in the numerator and the denominator, but not the most. But I think kind of what I always would call back to is if I had like 5 plus x divided by 10 is equal to 3, or some equation like that, the first step would be to get rid of the dividing by 10 by multiplying both sides by 10. And I'd say 5 plus x equals 30, and I'd carry on from there. But that's not the point. What I'm saying is the first step is probably going to be multiply both sides by x minus 16. And if I do that, pardon me, I'm not multiplying by x minus 16 on top and bottom. That'd be something different that we will do later on today. If I multiply by this on both sides, that's still fair. I'm going to be able to cancel these off, and I'd be just left with x squared minus 16. And that's still going to equal 0, because 0 times anything is going to be 0. All right, and then, okay, if I've got x squared minus 16 equals 0, we're kind of back into the realm of things that we're good at solving. I'm going to take the square root of both sides, not forget my plus or minus. I'm going to say x equals 4 and x equals negative 4. And I'm probably going to do this too. Okay, and so what this means is that we're going to be able to find the zeros of a rational function by finding the zeros of the numerator, at least maybe after we've canceled everything off. Okay. And then another takeaway is we need to practice solving equations that involve fractions, right? That's going to be still part of this class, and so we're going to need to do a little bit of more practice on it. So let's do that right now. Right, so here's another rational function. It's defined, kind of in an unclear way, but in a way that might be actually more useful in like a calculus class. But we're interested in finding the zeros, so we want to know where this thing is equal to 0. So I'm going to say 1 over x minus 1 plus 2 over x minus 4 is equal to 0. And we're going to need to combine these with a single denominator. And so I'm going to take 1 over x minus 1, and I'm going to multiply on top and bottom by x minus 4. So that'll be x minus 4 divided by x minus 4 times x minus 1. And then I'll be adding 2, whoops, pardon me. If I take 2 and I over x minus 4 and I multiply by x minus 1 over x minus 1, I would get 2 times x minus 1 divided by, again, x minus 4 times x minus 1. And now that I've got these things with the same denominator, I can add them into a single fraction. And then I'd be left with an x minus 4 plus 2x, whoops, pardon me, I lost my parentheses. I am going to be distributing the 2 over the x and the negative 1 right here, though. So I'm going to call that 2x minus 2. And I'm going to make sure to, be intentional about putting that stuff in parentheses, because if it was subtraction instead of addition of those two fractions, that would be something we need to be very careful on. Okay, and this is going to equal 0, but I'm going to do the collecting like terms right now. X plus 2x is going to be 3x. Negative 4 plus negative 2 is negative 6 over the same denominator, x minus 4x minus 1. Okay, and if this is equal to 0, I've got a single fraction, this is probably where I can grab the numerator, set it equal to 0, and solve. So I'm going to go over here and I'm going to say, all right, 3x minus 6 is equal to 0, and that would happen to be when x is equal to 2. So that's going to be the only 0 of f. Okay, now this other one here is kind of something that I would also remind you about. If we're going to find where two graphs intersect, we're going to set their formulas equal to each other and solve for x, right? So we're going to say x over x plus 2. I found the intersections of graphs in this class already. So maybe not with graphs of functions that involve fractions. So we've got this, and it is still valid to cross multiply if you've got fraction equals fraction. Nothing wrong with that. So x times x would be an x squared, and then x plus 2 multiplied by 1, well, that'd just be x plus 2. And if I've got more than one power of x in the same equation, I'm going to need to set it equal to 0 and hope to factor, and if not, then maybe I'll use the quadratic formula. So x squared minus x minus 2 is equal to 0. And I'm going to factor this thing, that'd be x minus 2 times x plus 1. And so that would be x equaling 2. Is that still on the screen? Yes, barely. And x equaling negative 1. Those would be two places where the graphs intersect. All right, now maybe you try it on your own. So here are 3 more rational equations, or at least equations that involve fractions, that I would like for you to try and see how they go. I'm going to just bring in the answers, though. So you're going to want to work this with video pause. So pause now, and then when you're done, check your work against mine. All right, there you go. So these were kind of interesting. The one in the middle really had a wrinkle to it. I still feel like that's kind of weird, but I kind of copied these from my Algebra 2 class last year, and we did a lot of solving of equations like these. We probably won't have to just like solve random equations like this. It's always going to be in the context of some kind of function, but it's always good practice. This is good algebra. All right, back to the functions. So the domain of a function f, unless otherwise specified, is going to be the set of all real numbers that produce an output that's also a real number. And so last year we saw that functions that involve like square roots, logarithms, or division by x could have a restricted domain. Okay, and for us, the domain of a rational function, unless otherwise specified, is going to be all x that doesn't cause the denominator of the function to be 0. So that means that we're going to need to take the values that do cause the denominator to equal 0 and throw them out. Okay, that's how it's going to work. So find the domain of h. So what we really need to make sure is that h is not causing division by 0. So we're going to look at the denominator, and we're going to find the zeros of the denominator. So x to the 3 minus an x to the 2 minus 2x. I'm going to figure out when that equals 0. Okay. And I'm going to factor that. I'm going to get a familiar polynomial. See, I'm not that creative. Okay, and the zeros of the denominator happen to be x equals 0, x equals 2, and x equals negative 1. So that means, those x values cause the denominator to equal 0. So they cause h to divide by 0 and therefore be undefined. So I'm going to say the domain is x is not equal to negative 1, x is not equal to 2, and also x is not equal to 0. Okay? And x is not equal to 2 only because it causes the denominator to equal 0. The fact that it makes the numerator to equal 0 is not relevant in this situation. Okay, that'll be a different discussion about what the graph looks like there. Okay, but either way, it's not in the domain, because just like some other number divided by 0, 0 over 0 is undefined. Right, and you need to know that the behavior of a rational function near an x value that's not in its domain will depend on whether that x value is also a 0 of the numerator or not. Okay, so for the function f equals p over q, if x equals a is a zero of q and not a zero of p, and f is in fully simplified form, then the graph of f has a vertical asymptote at x equals a. So what we're going to be interested in is, where does this thing have a vertical asymptote? Okay, well, we can do that. And vertical asymptote will be the zeros that are left over in the denominator after canceling. So I just factored the denominator of h. If you need to rewind and watch me do that, you can definitely do that. But I found that that was x times x minus 2 times x plus 1. And I have an x minus 2 in the numerator. Okay, so I can cancel off the x minus 2's, and I'm going to only do this once, but I'm going to say that this is equal to 1 over x times x plus 1 times, I've still got room, x minus 2 over x minus 2. Right? If I just did the multiplication of those factors, off to the side, it'd still be the same. We can multiply in whatever order we like. So x minus 2 over x minus 2, that's equal to 1, just as long as x is not equal to 2. So what we do is we kind of think about those as getting canceled. And I won't write it like that every time. I'll probably just like cross them off. But I'm just going to point out that this is equal as long as x is not equal to 2. That's not really what we're interested in right here, because we're talking about vertical asymptotes. And vertical asymptotes, zeros of the denominator that are left over after cancellation. So that's going to be from this one and that thing. So I'm going to say vertical asymptote. That happens at x equals 0 from the first factor, and x equals -1. And, because these are x values, these are also equations of vertical lines. These are the equations of the vertical asymptote. And so x equals 0 and x equals -1, the zeros that are left over after cancellation. And yeah, and then it's got that little note at the bottom. Message here is we need to continue to practice our factoring, obviously, and simplifying rational expressions, because simplifying rational expressions is one of the most error-prone algebraic operations. And I just want to make sure you're free from those types of errors. And honestly, the best way to be free of them is actually to make them, but with prompt and specific feedback on what you did wrong. So hopefully you can get those errors out during the practice, during the lesson, during the homework, but sometime before the quiz or the test, right? Right, so we should probably practice that, right? I'm gonna just do a little quick one, and then I'm gonna have you try to practice this on your own, because regardless of which type of Algebra 2 you took last year, this was definitely something you had to do, the simplifying rational expression. So I know that you have some experience with it, have had some success with it in the past. I just want you to remind yourself of what you've already accomplished. So I'm gonna do the first one, because it's already factored for us, and it'll be really quick. I've got the identical factor of x minus 4 on top and bottom, so I cancel that off. And then I'm left with x plus 5 over x plus 3. And I'm going to just put a little disclaimer over here that equality is true as long as x is not equal to positive 4. And we'll talk about what happens to the graph of the function, that's defined by that fraction at x equals 4 here in a minute. Okay, but I think you should do at least the next two. Now, these are the ones that are about, factoring and canceling stuff. So try the one in the top right and the bottom left. I don't really care about the one in the bottom right. I will copy in my answers, and then you can check your work against mine, but you're going to want to work with video pause like I was saying before. All right, there you go. So with these, a lot of factoring, a lot of canceling. I think most of my students this year are going to be good with this, but it never hurts to practice these. And so I've got 4 more, or at least some more down here. Yeah, we got 4 more. So I'm going to do the same thing. I'm going to work these with video pause. I'm going to bring in the answers here in a couple seconds. You can check your work against mine if you think you need. If you think you don't need, just skip ahead a few seconds. All right, there it is. Those were kind of a slog, but I think like I said before, it's good practice. It's good algebra. It's the type of skills that we need to have in this class. All right, now we need to talk about holes in the graph of a rational function. So consider the function f of x equals x squared plus 5x minus 6, all divided by x minus 1. So if I asked you about the value of f of 1, okay, we'd say, all right, well, f of 1, let's plug in 1 wherever I see x. So that's 1 plus 5x plus -6. It's going to be 0 on top, and then 1 minus 1 is 0 on bottom. Okay, so 0 divided by 0. Okay, I'm just going to tell you right now that is not a real number. I already mentioned it once, and I will be mentioning it repeatedly. This is not a real number. It's not equal to 0, it's not equal to 1. So we would say that f of 1 is undefined. And you could also write d and e, that would be just fine. Okay, and then sketch the graph of y equals f of x. Now, what I'm going to show you is that when we get 0 over 0, it's oftentimes because we are we're sitting on a hole in the graph, which is also something that we talk about in Texas Algebra 2, and I'm not sure what your Algebra 2 experience was, but we definitely had holes in graphs in my Algebra 2 class that I taught last year. So I know that the people that were in my class have some familiarity. I'm going to be able to factor the numerator. I think it's going to be x plus 6 times x minus 1, yeah, divided by x minus 1. Okay. And then I can cancel off those x minus 1s, so this is equal to x plus 6, provided that x is not equal to 1. Okay, so we can sketch that graph. Okay, we know what the graph of y equals x plus 6 looks like. I can actually extend my axes and make them nice straight lines. So let's do that. Okay, that's a pretty straight line, and then I think I want the y-axis to be pretty much in the middle. Okay, that's good. Then I might actually draw this in. No, I'm not going to have it snap to a line. That's too risky. Draw a line with a positive slope, slope of 1, and then a y-intercept of 6, and then at x equals 1, it's removed from the domain. But at all other points, it's y equals x plus 6. And so it's just a line with a hole in it. And not just like we would expect, the y-intercept is going to be at x equals 6. That's the 0 of the numerator that's left over after cancellation. But what I'm going to point out is that we can also find the y-coordinate of the hole using kind of the formula that's left over, this x plus 6. Okay, because although the graph is not there, we know it's really close to that. And so we're going to say, at x equals 1, we could plug back into the simplified version of f of x, or whatever we're calling it, and we'd say 1 plus 6 is equal to 7. Okay, so the y-coordinate of that hole is 7. And then the notation we're going to use is, it's a limit. Although we're not really defining the meaning of the limit in this class, we are going to be using notation. So the limit as x approaches 1 of f of x, that's going to be equal to 7. All right, now one other thing that I need to tell you about is that we can say that the limit of f is equal to 7, although f of 1 doesn't exist, because the graph of f is getting arbitrarily close to y equals 7 the closer x gets to 1. So from the left side, y is approaching 7. The notation for that is the limit of f of x as x approaches 1 from the negative side, which really just means like the left-hand limit. Okay, and then that's going to be equal to the value of the right-hand limit, and we denote that using the limit as x approaches 1 from the positive side, right? Like out here, this is where x is more positive than 1. Okay, and off to the left, that's where x is negative. Okay, so that's why we use that notation. But you need to be kind of familiar with that notation, but we'll be doing a lot of work with limits in this unit. Alright, so our rule is if x minus a is a factor of both the numerator and the denominator of a rational function, and the multiplicity of that root in the numerator is greater than or equal to the multiplicity of that root in the denominator, then the graph will have a hole at x equals a. And there's that sentence is a little redundant. Definitely going to be changing that for the PDF I published on the internet. Find the locations of any holes in the graph of the function. Okay, gladly. So what we're going to do is we're going to find the x-coordinate by looking and seeing, okay, what did I cancel off here? So right here I've got a factor of x minus 1 that's common to top and bottom. So f of x is equal to x plus 3 over x minus 2 as long as x is not equal to 1. So that means as far as like looking for a hole in the graph, that would be at that excluded value at x equals 1, and y would be equal to, I'd plug 1 in everywhere I saw x in the formula that's simplified. So it would be 1 plus 3 divided by 1 minus 2, and that's going to be 4 over negative 1, and that's negative 4. Okay, so the whole is at 1 and negative 4. And over here, I'm going to do the same thing. G of x equals x to the 3 minus x over x squared minus 5x minus 6. Okay, we're going to need to factor this one first before doing any canceling, because I have to be canceling factors that are multiplied. That's what a factor is something that's multiplied together. So I'm going to factor out the x and be left with an x squared minus 1, which I'm realizing I could go a little bit farther on. And then this one's going to be factorable. We just got to be careful with the 5 and the 6, right? That's kind of another message I've got for you in these notes. So x squared minus 5x minus 6, that's going to be negative 6 and positive 1. Right, and then that makes sense. That's going to continue to factor in the top, x times x plus 1 and x minus 1 divided by x minus 6 and x plus 1. You can see the x plus 1s are identical factors on top and bottom. So I'd say this is equal to x times x minus 1 divided by x minus 6, just as long as x is not equal to negative 1. So I know that that means I've got a hole in the graph at x equals negative 1. And then the y-coordinate I'll get by plugging into the simplified version right there. So I'm going to say, all right, negative 1 in the numerator multiplied by negative 1 minus 1 is a negative 2. All divided by negative 1 minus 6 more is negative 7. That's going to be 2 over negative 7, so negative 2/7. Coordinates of my whole are negative 1 and negative 2 over 7. Alright, now, like I mentioned when we were looking at the graph of the line with the hole in it, we're going to need to be able to compute these limits with algebra. And although I'm not certain if in AP Pre-Cal we will be confronted with just like a direct limit like this, it is exactly the type of thing that we need to be able to solve, and it's the type of problem you'll need to be able to solve in AP Calculus next year, and so I figure why not get started right now. But this, what we're doing is we're finding the y-coordinate of the hole in the graph of the function defined by that fraction at, on the left, x equals 0, and on the right at x equals 2. What we're going to do is we're going to solve this by factoring and canceling, just like before. So if I was to plug in, and that's actually, I'm going to take a step back. So my advice to you whenever you're confronted with here's a limit, figure out what it is just try plugging in first. Especially if x is approaching a real number. You can't plug in x equals infinity or negative infinity. That isn't really going to work. But I'll talk more about those here in a couple minutes. Okay, as x approaches 0, okay, if I tried to just plug in on this would go towards 2 times 0 plus 6 times 0 over 4 times 0 plus 3 times 0. A bunch of zeros. 0 over 0. That's not equal to 0 and not equal to 1. It's not equal to anything. It's an indeterminate form is what we call it. But for us, we know that means we're probably sitting on a hole in the graph. And so what we're going to do is we're going to factor the numerator and the denominator. So I can see a 2 and an x cubed, because I know I want to cancel. I'm going to be like writing everything that's multiplied together in parentheses. 2x cubed times x to the 3 plus 3 more. Yeah, okay. And then in the denominator, we're going to factor out 3 powers of x. We'll be left with 4x squared plus 3. Okay? And what we need to do, and this is another thing I'm not sure about with AP Pre-Cal, I'm pretty sure we would not be asked about this limit in free response. In fact, I'm more or less certain about that, at least for the time being. But we need to maintain that limit notation right here. Okay? If we didn't, that would be what is called a linkage error. Because that limit is not equal to that expression in x, which would not necessarily be always equal to whatever we're going to get after we cancel. So we just need to maintain our limit notation, and it's kind of just a presentation issue, which is something that I'm just kind of starting in with you now, and it's something that's built up over time, building that mathematical maturity. So we're going to cancel off those identical factors of x to the 3, and this is it's actually a theorem from calculus, but I think that y'all would not disagree that the limits of these things are going to be equal after the cancellation. So I'd be left with a 2 and an x to the 3 plus 3 over 4x to the 2 plus 3. And since I don't have identical factors on top and bottom, I will not be able to cancel any further. Okay, but once I can't cancel anymore, I should try plugging in again. And if I do that, I'm going to get 2 times 0 plus 3 when I plug in x equals 0 over 4 times 0 squared plus a 3. So that's 6 divided by 3 equals 2. And that's how we compute these limits algebraically. It's going to be by factoring and canceling. All right, so I think it's time for you to try this one on your own. Work this one with the video pause. I'm going to bring in the answers in 5 seconds. All right, there you have it. So I plugged in initially, I got 0, 0. Okay, so I know that that probably means I need to factor and cancel. So I factored them, I found those identical factors, canceled them off. I'm left with x plus 3 on the top, x plus 2 in the bottom. After canceling, I'm going to try plugging in x equals 2 again, and I'll get 5 over 4. Okay, so that's good news. Another one I got for you. This is the exact same type of problem, except they decided to write this one as a sentence instead of just a, here's a math problem, have at it. And so what we're going to do is we're going to try plugging in x equals 3, right, because that's the value of x that we're approaching. And I'm going to get 3 squared is 9 minus 9, so it looks like I'm going to get 0 over 0 again. But you don't always, okay, so that's why we always try plugging in. It's not always necessary. 3 to the 2 is 9, plus 6 is 15, minus 15 is 0 and 0. Okay, so we need to factor and cancel. So I go over here and I'm going to say, all right, I'm taking the limit as x approaches 3 of, okay, factor the top, factor the bottom, factor the top. I have not factored the bottom yet. That's going to be x plus 5 times x minus 3. Okay, look, we've got these factors canceling. I'm going to try plugging in 3, and I get 6 over 8. That's another one of these. All right, I got another one for you. So f of x equals x minus 2 times x squared minus k squared over x squared minus 4 times x minus k, where k is a constant. They're going to ask for what value of k, if any, does the limit of f as x approaches 2 equal 3. And this is just a little bit more challenging. But what I want to propose is that we can solve this the same way we've been solving all the rest of the problems like it. We're going to factor and cancel. So if I've got x squared minus k squared, I can factor that into x plus k and x minus k. Then x squared minus 4, that can be x plus 2 and x minus 2. So I see there's going to be some stuff canceling. And I still have that x minus k over here. Okay, so I'm going to cancel those x minus k's. And then I'm going to cancel the x minus 2's. And so I'm going to say, all right, so this limit as x approaches 2 of f of x is going to be the limit as x approaches 2 of x plus k over x plus 2. Say this needs to equal 3. So now when we go and plug in on the limit, 2 plus k over 2 plus 2 is 4, that still needs to equal 3. And so this is the type of equation I was talking about way earlier that we would solve by multiplying both sides by 4. So that means that 2 plus k is equal to 12 and k is equal to 10. Okay. And that was just an interesting question I found in AP Classroom. Okay, takeaway is limits are a recurring theme in AP Calculus. We're going to have a variety of types of limits. We need to practice all of them. So, in conclusion, let's do some of that practice. Okay, remember that we've already seen limit notation in this class to denote the end behavior of a polynomial. And that's what we're seeing on the left side of the left column, okay, over here. And notice that it has to do with when x is approaching infinity or negative infinity. When we see that, we're going to think end behavior, and remember that is determined by the degree of the polynomial and its leading coefficient. And the ones in the right-hand column, these are limits that involve factoring and canceling. So you should try all 6 of these with the video paused and check your work against mine. All right, there you go. So that was some good limit practice, but we will get a good amount of limit practice in with all 4 lessons in this unit. So this is going to be a recurring theme. We will get our practice. Don't worry about that if you're struggling with it right now, because it's just like, give it time and it'll get better. Yep, so that's going to be all for this lesson. Thanks for watching.